So we discussed the difference between conservative and non-conservative force, and we looked at the path being independent, and conservative force looks for displacement, while non-conservative depends on the distance, the path actually taken. So when we have a closed path, there's no work being done. So I want to explain on that. So let me do this. First thing is, let me explain closed path. So you have a starting point A, B. If I happen to travel along this path, right, say path 1, and if I happen to come back to point A, that's path 2, what we have here is a closed path. This is an example of closed path. So, and if this happens to happen, all of this happens to have happened in a conservative force, then the system's energy gain, change in the energy of the system. When I tell system, the object over here, change, okay? Change is 0 joules. There's no change in the energy. So first thing is, what is a closed path? A closed path is a path that starts and ends at the same point. So conservative force in a closed path, if a conservative force acts on an object and the object moves around and returns to the original state, the energy will remain same. That is, there is no loss or gain in energy. It is 0 change in energy. So proof, I will be going case by case. I won't be doing here because it's kind of weird and it's like a self goal. I mean, we are using the same thing to prove it. So for me, at least it didn't make sense. So not to that extent. So I'll do the proof case by case. Okay, then with the proof, we'll be able to conclude that a conservative force is one that conserves mechanical energy. The key points are that path independent, which we saw. Work done by a conservative force depends only on the initial and final position, not on the path taken. Right? So, we didn't see that per se. So what it means is path independent. So if I happen to move from point A to point B, right, in against the conservative force or in the direction of conservative force, whatever that is. So basically, if I move from point A to point B and you have conservative force around, it won't matter how you went to point B. Like we saw the phone case, I spoke about this repeatedly. So if we happen to drop a phone from point B, doesn't matter how you reached point B, the damage will remain the same, right? That point. So closed loop test, the total work done on a closed loop is 0. So if you want to test if the given force is a conservative force, then you guys have to make it go through this. You can test with path independency, we can test with closed loop test. And finally, potential energy, the conservative force allow assigning numerical potential energy value at any point. Okay, again, all of these points will be commonsensical once we go to the actual conservative force like gravity, spring and all of that. Then it will make a lot more sense. Okay. So for now, please copy this. These are important property of your conservative force. It's very much useful for your numericals. So yeah, and we'll do the proof. Don't worry, we'll do the proof. So someone who wants to draw this can also draw. And make this point as well.